If you have questions about the questions, ask me a question. If there's a notation question, ask me. I might not answer, but you can ask me anyway. Yes? That's this thing I forgot to write here. That's F. Sometimes people write that as a capital N. It's the fixed or the Newtonian frame. Are those T's what? With respect to truck as opposed to with respect to fixed frame. So oftentimes people call the moving frame B for body. Yes?
What are x of t and y of t? Is that a function?
By the way, that's meant to be x prime of t and y prime of t. And this is at time of interest. Thank you for all those so far, so please ask more. If you want to think about it, here's the truck. It's a cardboard model. I think I made it back when I had that 63 Ford, which I showed you the picture of. Here's the x prime axis. Here's the y prime axis. And we're trying to keep track, little body work on this old truck, trying to keep track of the motion of some point which is moving around in the truck. I still have dreams about that truck, but now that I realize I have this cardboard model, I can just leave this out and think about the truck with this cardboard model. You'll see, you'll have dreams about your first car too when you get old. Okay, you ready? Yes? Is the point what? Better be. Well, I don't know. I mean, that's what this stuff is supposed to be about. How you guys doing? Who wants more? How about we'll do it this way? Everybody vote E. I'm going to assume some of you are not going to vote E in the end. Or is the vote not turned on yet? Okay. The vote's not turned on yet, so vote when you're ready. And when enough people have voted, then I'll count down to 10, and then you'll be done. Blocking your view. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. There you go. So let's work it out. What? Oh, sorry. Were you voting E because I told you to vote E? Oh, sorry about that. Okay. Now vote what you want. I'll turn the sound off on my telephone. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. There you go. Okay, so now let's work it out. So this is a vocabulary question, obviously. And the big question is, what do these symbols mean, and how do we figure things out with these symbols? So the problem is, and we're using the truck as an example just because it's easy to visualize, but you want to think about it in the end that replacing this truck is just some link in a machine on which, in principle, you could draw a whole coordinate system and so on. Now, if you've just got a little link in a machine, it's hard to picture a coordinate system. So what you want to do in extending this idea is every little rigid part, you want to imagine that glued to it is a giant piece of plexiglass on which coordinate axes are drawn. And whenever you talk about motion relative to a body or on a body or something, you're talking about motion relative to that plexiglass coordinate system which is moving around with the object. And we start with a big object so you can picture it easily, but for any little object, there's some massless, rigid plexiglass with a coordinate system on it. It's called a frame because you draw those, I don't know if this is why, but I'm making this up, but it seems to work, because you draw those lines on it and it looks like a structural frame. The graph paper looks like a frame, especially 3D graph paper, and this idea works in 3D. So you draw that coordinate system, it moves rigidly with the object. You can think of it as connected to plexiglass, or if it's in 3D, it's a giant piece of massless jello with coordinate lines drawn in it, and each piece has one. And the jello all interpenetrates, and it's very hard to picture. So, but anyway, 2D is easier to picture. Okay, so now we have this concept of motion relative to a frame. Okay, so that's what we're working with here. Let's just use this dot here to start with. The motion relative to a frame is measured, the simplest way to think about it anyway, is to draw a coordinate system fixed to the frame and look at how those coordinates change in time. So how do the coordinates of this point change in time as this truck moves around? It doesn't. So points that are fixed in the frame have zero velocity relative to the frame. If this point was moving in a straight line like this, I drew some line on here, and this was a bug, and it was a circus bug, and I trained it to follow lines. It would follow that line. It would be going in a straight line. Now, when you watch it in the room, you see a bug moving like this. What's the velocity of the bug in the truck reference frame? It's always parallel to this line, whatever the instantaneous direction of this line is. So the velocity of this bug in this frame is in this direction, even if the truck is moving like this. So I'm moving the truck up and down like this. Let's say I'm moving the truck fast up and down like this, and the bug is crawling slowly in this direction. The velocity of the bug relative to the frame is slow in that direction the whole time. What about acceleration relative to a frame? Is you calculate the acceleration as if this coordinate system was a good coordinate system, a good Newtonian Frame system. It's not. But you pretend it is, and you calculate, for example, x prime double dot, y prime double dot, multiply each by unit vectors, and it gives us a vector, which is the acceleration relative to the frame. For this thing sitting right here, when I go take this whole thing going in circles like this, that acceleration is 0. On the other hand, if this thing is going in circles like this, round and round in circles like this, and I carefully move the truck round and round in the opposite circles, so the bug stays still. So watch this point here where the tip of my finger is. So there's a bug right at the tip of, I've got a circus bug trained to follow my finger crawling on this truck. Its velocity is 0 down here in the room. Its acceleration is 0 down here in the room. But its acceleration relative to this frame is not 0. It's what we get by doing the circular motion formulas. And the velocity relative to the frame is not 0. And we calculate by looking at how the x prime and y prime coordinates change in time and multiplying by unit vectors in those directions. Now those unit vectors are going to change in time. So when we calculate that relative velocity or relative acceleration, it will be a vector expression with crooked unit vectors. And when we want to evaluate it down here in the room, we're going to have to turn those crooked unit vectors and find the components in terms of the regular vectors and so on. Okay, so now let's take that with this problem. Well, let's see. We're given that this truck is moving in that direction, and it's moving with an acceleration in that direction, so the truck is accelerating that way. We're given that it's rotating at constant speed. So this truck is not rolling. This is like my truck on the ice just before it crashed into the ditch. It's moving that way, but rotating that way. It's going like that, sliding along. It's got no rotational acceleration. We're given that this x prime dot is 1 meter per second is constant, y prime dot is 0. This being constant says that the velocity relative to the truck is not 0, right? It's something. It's 1 meter per second. So the velocity, this one is wrong here. It says that it's not 0, but it doesn't happen to have a y component. At the instant of interest, it's got some position. Who cares? Now let's look at these other things. Is the velocity at this point 0? No, because the truck is moving along. Let's see, the truck's going 3 meters per second I. This is going 1 meter per second. It can't possibly cancel even if the truck is pointed backwards. We weren't given what the theta was at this instant, but it still can't cancel because 1 is smaller than 3. So this can't be true. The acceleration relative to the truck is 0 or not 0? 0, because this is constant. Okay, so this is good. And the acceleration relative to the fixed frame is 0 or not 0? Not 0. So this is good. And so we're happy here with B as our answer. And how did you guys do? Yeah, you did okay. Then we close this one up, and we're all done with iClicker for today. Okay, so now let me go back to these formulas. So we have the position of P, and usually we might just write position of P. Implicit when we write in position of P is relative to O. So whenever you write a position vector, you don't write a subscript, you mean relative to O. Whenever you write a velocity or acceleration and you don't write a subscript, you mean relative to the fixed or Newtonian frame. But now we're going to sometimes have to be careful about that. This is the position of O prime relative to O plus the position of P with respect to O prime. Then I said we get this velocity relationship. What is the velocity of P, or the velocity of P relative to O? That's the velocity of O prime with respect to O plus the velocity of P with respect to the truck frame. And in the general formula, we're going to call this the body frame, B for body, plus omega crossed with the position of P with respect to O prime. And whenever we write omega, we mean the obvious omega, whatever is in sight. In this case, we're looking at omega of the body relative to the fixed frame. Okay. I'm not deriving this formula for you, but I convince you, or try to convince you, that it's true by saying that we have to have at least terms like those terms there. Why do we have to have terms at least like these terms here? Is we imagine the bug is glued to the truck, so this thing is 0. It will have a velocity even if one point in the truck is pegged to the ground, because the bug is spinning in circles with the rest of the truck. So even if we peg this point to the ground, if the bug is glued to the truck, it still has a velocity, and that's that omega cross r. Yes? What, say again?
Why is it p with respect to beta, not p with respect to alpha?
Okay, so this is a very important point. If I write velocity of p with respect to O prime, implicit in that is that I'm writing the velocity of p with respect to O minus the velocity of O prime with respect to O, and that all of these velocities are in the relative to the fixed frame. So if I don't put any subscripts about reference frames, I mean by that position. Just a minute. What's the problem? What's the one you didn't want? It's right here. If I just put VP with respect to O, then I'd be done with this formula. Because that would just mean the rate of change of the vector from here to here. And this velocity relative is not the rate of change of that vector. So this whole thing is that thing. I don't know if I addressed your question or not. Who asked the question? Did I get it? Did I get it or not?
Kind of. I just thought you were writing it as p with respect to O prime, and that's equal to omega cross r.
Yes. I could copy down from here. This goes to V O prime with respect to O plus V P with respect to O prime. And if the bug was glued to the truck, that would just be this term. Now we want to include the possibility that the bug is not glued to the truck but is walking around, and then I get this extra term. Who asked the question? Does that do it for you then? Okay.
Is the O prime is our body reference frame?
Oh, well, O prime is the body reference point, but the body reference frame, the truck frame, or if I wanted to call it in general, I'm using a script B, not beta. This is equal to O prime, I prime, J prime. It's this whole collection of things. It's not just O prime, because O prime is just a point, and the frame includes an orientation as well. Right, you could imagine multiple points that had the same, multiple trucks that had the same O prime, but rotating different amounts, and those would be different reference frames. Does that address your question? Any other questions? Okay, and then we get to this crazy formula, which is what is the acceleration of p with respect to O. And I'm just going to write this formula out, and then I'll tell you a joke about it, and then we'll work with it. Okay. It's the acceleration of O prime, which we could write as the acceleration of O prime with respect to O, plus the acceleration of p with respect to the body frame, plus omega cross the position of p with respect to O prime. And in 2D, which is all we're doing in this course, this is equal to minus omega squared, the position of p with respect to O prime, plus omega dot crossed with the position of p with respect to O prime, plus 2 omega cross v of p with respect to the truck. And as I said, someday you'd like to understand how to derive this, but I think it doesn't make sense to derive it until you understand what it says and are used to using it. Now, when I first saw that formula, I thought it was a nightmare. And I thought, I'm never going to learn it. I don't like it. Blah, blah, blah. It stinks. Then I got to Cornell and I became a professor. And professors were doing this thing that professors do, which is they whine about students. And one of the faculty members, Professor Moon, who's now just retired, said, oh, the students nowadays, they don't even know the 5-term acceleration formula. And I said, oh yeah, the students nowadays, they don't even know the... I don't know the 5-term acceleration formula. I don't even know what you're talking about. So I decided I should learn the 5-term acceleration formula. Then I thought, this is a great formula. And then in the early years when I used to teach this course, I used to think that this was not only the hardest formula, the most important formula, this was the key thing in the class. So one time when I taught this course, I wrote this formula on the blackboard. I wrote this joke in the book too, so you can read it there. It's a true story though. I wrote this formula on the blackboard in giant letters all the way across, and I circled each term and I explained what it meant, and I had the derivation, and we spent weeks leading up to it. And I wrote it all down there, and I said to the class, and this was back in the old days when they didn't have ventilation systems like this, so you could actually have rooms that were quiet, so there was real intensity, and you could hear a pin drop, and it was all up there, and the room was totally quiet, and I said, this is it. This is what we've been leading up to. We've been building up to this and building and building, and we finally got there. This is the climax of the class. Totally quiet. And this kid in the front row goes, was it as good for you as it was for us? That is a true story. Okay, so here's this formula, which is a nice formula. Lots of people like it. It's complicated. It's hard to understand. I no longer think it's like the greatest thing since sliced bread, or the greatest thing, whatever you want to think about. It's just a nice formula for understanding relative motion. How do you think about this formula? Yes? Say again? That's script B for body. Say again?
The one before it?
This one?
No. The 2 pieces of subscript on
P. We're always looking at P, 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 except for O prime. Okay, so we want to understand this formula a little bit. What's it about? It's about this thing of relative motion. It's about, you can imagine it goes like this. You have a friend who's on the body, even if it's a little machine part. They're keeping track of things by saying x coordinate now is 3.68, x coordinate now is 3. And they're using this x prime coordinate. They're keeping track of the x prime and y prime coordinates as a function of time. Therefore, they know the velocities in their crazy, screwed up reference frame as a function of time. They know the acceleration in their crazy, and they always report that to you. And there they are on this spaceship, this truck, this machine part, reporting to you constantly what they think the velocity, position, velocity, and acceleration are. And they think it by measuring these x prime, y prime coordinates. You're down there looking at them and going, man, you're all screwed up. You don't have it right at all. But you know where they are. And you want to figure out what the actual acceleration is. And what this formula is correcting for the fact that they're giving you good information and their screwed up way of looking at things, and you correct for that. That's what this formula is about. Now, how can you understand all these different corrections? Each one makes sense in itself, except for the last one, which is a little hard to understand. So I'm going to try to explain to you each of the terms in this formula with this truck. Are you ready? First off, how are we going to do this? We're going to try to find situations where we can cross off all but one of the terms. First situation, we're going to look at a bug on the truck. So the thing we're going to keep track of is a bug. Actually, we're thinking of some machine part or some part of some machine part. We use a bug to make it a cartoon. The bug is glued to the truck. Now let's say the truck has no acceleration. It's going at constant speed. Maybe it's still. It's not rotating. Bug's not moving. Okay, the truck is not accelerating. Therefore, the bug is glued to the truck. There's no relative acceleration. The truck is not rotating. There's what we get here. I think I killed all five terms just now, didn't I? I don't want to kill quite all five terms. Okay, the truck is going to accelerate, but it's not going to rotate, and the bug is glued to the truck. Okay, the truck is accelerating, we have this term. The bug is glued to the truck, this one's gone. The truck is not rotating, this term is gone. It's still not rotating, this term is gone. It's still not rotating, and the bug is glued to the truck. This one is gone twice over. 0 squared is super 0. All we get is the acceleration of the truck. First term. Now, let's just say the truck is not rotating, is not translating, so there's no acceleration of this reference point, so all we're going to be looking at is rotations now. Okay, what's the simplest thing we can do is let's have this point still. We got this gone. Let's have the bug glued to the truck. If the bug is glued to the truck, this term is 0 and this term is 0. All we have left is these two terms. What are those two terms? Those are just the polar coordinate formulas for acceleration of a bug going in circles around this reference point. The truck is still, or at least this point on the truck is still. It's rotating. The bug is glued to the truck. What's the acceleration of this point? It's got an omega squared r and an omega dot cross r. Those are these two terms. We could get one at a time by saying omega dot is 0. The truck is just spinning in circles. We just get this one. And we could set omega equal to 0 and start accelerating it, and all we get is the tangential one, this one. So now we've got this one by itself. Truck moving, the bug is still. This one by itself, truck is still and rotating at constant speed. This one by itself, truck is still, bug is glued to the truck. Truck has 0 angular velocity, but it's starting to accelerate. So each of these terms makes sense. What about just this term? Well, just hold the truck still and have the bug run around, and then the acceleration of the bug is the acceleration of the bug, because the fixed frame and the truck frame are the same if the truck is still and not rotating. So now we've got this term. So now we're left with this horrible term. What's that about? It's the same as the 2 theta dot r dot term in the polar coordinates. It's about the following fact, that if the bug is going in a constant speed in a straight line, and the truck is rotating at a constant rate, and let's say the truck isn't even accelerating, so the truck is not accelerating, is rotating at a constant rate, so this term is 0. Let's just say the bug happens to be passing through this point here, therefore this term is 0. The bug's going at constant speed relative to the truck, so this term is 0. The bug's going at constant rate, so this term is 0. So imagine a bug, for example, walking on the x prime axis, passing through this point, and it's going in a straight line relative to the truck, but relative to the fixed frame, it's going in a curved path. So it clearly has some acceleration, and this is a term which catches that acceleration. Say again? I'm going to say that again. Let's start out with a bug which happens to be walking along the x prime axis on this truck. And the bug starts over here, and it's walking at constant speed on that x prime axis. It happens that God came and put a spike through the back of my truck and said, no more experiments for you. Your truck is stuck to the ground right here, and all the truck can do is spin like this. Now, it's very slippery ice. Somebody came along and said, you're a lousy truck, and they gave it a shove, and the truck is spinning around this spike at constant rate like this. Well, the bug is walking at a constant speed along this line, which is a straight line relative to the truck. In that situation, the acceleration of O prime relative to O is 0. Here's omega dot is 0. The position of the bug relative to O prime is 0, just as it passes through this point. The only term which is not 0, I don't know if I got them all, but the only term which is not 0 is the last term here, which is called the Coriolis term. What's the job of that term is to account for the fact that a bug which is going at constant speed on a straight line on the truck actually is moving in a curved path in this fixed frame, so it has some acceleration. So if all we did was to have these other common sense terms, we'd miss the fact that there's an acceleration due to the fact that constant speed straight line motion in a rotating frame is not a straight line motion in the fixed frame. Does that address your question? Okay, so now you'd like to be able to do problems with this. This is not a formula that you have to use. There's usually ways of circumventing it. It now just gives you another way to do problems. And you should learn how to use it so you have it available to yourself. So let's imagine that we have this slider crank situation. Which some of you do have in your machines. And what we're going to do is we're going to call this, in this way of looking at this thing, which is not the only way to do this, it's just a way to do this, is we're going to call this the body frame. And that means associated with this point, with this body, we could draw an x prime and a y prime coordinates, whereas meanwhile down here we have our I and j like this. Now, in this body frame, we're going to pick a origin, and we can pick whatever origin we like. I'm going to pick this as my origin. So maybe I should draw the y prime up here. I can pick whatever I want from my origin. Actually, I can orient the graph paper any way I want to. I don't have to line it up with the truck or the part. It's just usually convenient to do that. Now I'm going to keep track of angles here. I'm going to keep track of this angle this way. I'm going to call this theta, so it's not going to be my usual polar coordinates. I'm going to call this distance r. I'm going to call this distance L. And for this purposes, I'm going to call this point P. As this thing rotates around, this has a rotation angle phi. Okay, now let's say we're given the puzzle, which is the following puzzle. Given, well, we're given the machine, so we're given R and L. Let's say we're given the configuration of the machine. We're given theta and phi, which is tricky because these are not independent. They have to be set up so that that point P is right on the x-axis where we want it to be. And we're given theta dot and theta double dot, and we're asked to find, we're given phi and phi dot, and we're asked to find theta dot and theta double dot, because we want to do some kind of mechanics calculation. I shouldn't have pushed that up because surely I'm going to want to correct something over there. So how can we make sense out of that? Yes? You don't like the way that I spelled phi dot and phi double dot. Any other mistakes? Yes?
I'm just wondering, so the y prime and x prime coordinates are along the direction of each of the bars? Or?
The x prime and y prime are my body coordinates, which are glued to this piece, which I call the crank. And I pick them to be aligned with parts which are marked on the crank. And this part, which I've marked on the crank, I'm calling it O prime. So I picked it. It's glued to the crank. And if it's glued to it, I want to do useful calculation, I have to say how it's glued. So implicitly in the drawing, it's supposed to show that X prime is lined up with the line O prime.
So theta isn't supposed to look like the angle between X prime and Y prime?
We don't know I have not put any coordinates here. So I guess this is Murphy's law of drawing, right? Theta is not equal to pi over 2, and I should draw this like this, which is not lined up with that. Sorry. I'm sure you all fall into Murphy's law of drawing too. Murphy's law of drawing is 2 points or 2 lines that you do not intend to be coincident or parallel will be. Especially bad in 3D. Okay, yes, so I did not intend this angle to look like a right angle, and it does here. Does that answer your question? Okay. So now the way we're going to solve this problem is by, okay, you guess what I'm going to write on the right-hand side here. I'm going to count to 3, and everybody say it at once. 1, 2, 3. That was a good guess. Okay, let's forget 0. That works lots of times. But in this class, we have a different thing. Okay, 1, 2, 3. VP, right. What are you laughing at? It's just so stupid to write an equation like that. Is that what you're thinking? But this is how you solve problems. Why does it work like this? Is because we know that the velocity of p is vp in the I direction. So we know something about it because of that constraint on the right-hand side. On the other hand, we have a different way to think about the velocity of p. It's something which is moving around relative to this crazy coordinate system. So we can now calculate the velocity of p in terms of this crazy coordinate system. So we can say it's equal to the velocity of O prime with respect to O plus omega of this body crossed with the position of p with respect to O plus the velocity of this point relative to the moving frame v. Now we have to figure out what each of these terms are. Yes? Say again? O prime. Now we're going to assume that we know how to do some geometry, and I'm not going to do all of that geometry here. So I'm going to assume that you can calculate this from the picture. And you can calculate it in any coordinate system that makes you happy. What is this omega of the body frame? In this case, that's the thing I called phi dot k. What is the velocity of O prime with respect to O? Well, this is phi dot k crossed with the position of O prime with respect to O, which is something else using this geometry that you can calculate. And then what is the velocity of p relative to the moving frame? This is the new hard concept. And this is what? Well, this is rotating about this frame. What is it? It's rotating with angular rate theta dot k. And then we can take the cross product of this with the position of p with respect to O prime. So the geometry lets us calculate all of these things. We're given all the rest of the things. So this is a formula that has in it as unknowns. Well, what's unknown in here? This is unknown. And what else is unknown here is this is unknown. if we take this equation and take the dot product of both sides with j, this will give us one equation to solve for theta dot. Yes?
Can you elaborate on the BP vector data term?
Okay, this is script B for body. It looks a lot like a beta, doesn't it? I should draw it. Okay, strict B for body. Where does this come from? We get on board the body. So we get on board this crank. And as this is cranking around, we're turning our head like this, and we're looking at what is the velocity of this point relative to us on this body. On this body, if you want, put a truck up here. On this truck, this thing here is just going in circles. Who asked the question? I just want to make eye contact. So this point is going in circles relative to this reference frame.
So
What's its velocity relative to this frame is we just use omega, and relative to this frame, that's theta dot, cross the position.
Okay.
Does that work for you?
I think so. I just
It's hard.
usually you've written velocity to some point as omega cross r with the same subscript. This time you switch b with respect to b to b with respect to o prime.
Right, because now we're doing this crazy thing. It's a whole new concept that started last lecture, is keeping track of things relative to a moving reference frame. And so when I use relative to a point, then I always had implicitly using some fixed reference frame.
Okay, so it was implicit before and now it's
Now I've got to be explicit about it because I get different answers depending on which reference frame I use. Okay, now what's the next thing I can do? Okay, 1, 2, 3. 1, 2, 3. AP. Okay, what's your question?
What's the difference between writing like B with respect to B versus B with respect to
That's what we're talking about here in the whole class. V of one point with respect to another point implicitly is a calculation done in the fixed frame, and it's the difference between the two. So when you say, what's the velocity of one point with respect to another, it means 1 point. Relative to another means 1 point minus the other. Relative to in English means minus, and relative to in this course up to this point means minus. So it's the difference between these two velocities as you see it in this room. This v relative is not the difference between these velocities as you see it in this room. It's the difference between these two velocities as seen by somebody in this moving truck. And that's not the same thing. For example, if this second point is still, and this first point is still, and the truck is rotating, a person on the truck will think there's a relative velocity, even though you in this room say Vp with respect to O prime is 0. So in this particular example, I'm showing you here, Vp with respect to O prime is 0, but Vp with respect to the truck is not 0, because a person on the truck sees this thing going back and forth. That's what the whole lecture is about. I think I've explained it about 5 times, which doesn't mean you should have naturally got it already, but that your question is exactly the thing you have to understand the formulas in this course, in this little section of the course. So it's a perfect question. I'm sure half the people in the room are confused about it, but watch the video, read the book, work on some problems. Okay, I don't have time to expand this out here. I will expand it in the notes, which I'll post online, which will just show you what the equivalent of this thing.